second lecture of our example number 2 of foot over bridge, which is the warrant type of foot over bridge. Okay, and it is already told that this is our second example, in which our first example is for N type of foot over bridge, and there are most of similarity in N type of foot over bridge and W type of foot over bridge in design. Say for example, in N type of foot over bridge, our top chord in through type of bridge, our top chord is designed for compression member, our bottom chord is designed for tension member. So the design of tension and compression members is similar, but first of all we have to find out forces, and after the find out forces, the design will be remain same. Okay, so let us revise in the last lecture. This is our second lecture. So in the last lecture of our example number 2, we have to cover up to our section selection. So in the last lecture we have to cover, like, so you can see that our examples data is design a steel foot over bridge for the following data, and in this data you can see that our type of truss is warrant type, span of bridge is 18-meter long. Okay, after that the next data is width of walkway, which is 4 meter. Panel length, now panel length is given as 3 meters. So if our span is 18 meter and our panel length is 3 meter, then there is 6 panel of 3 meters. Okay, so in the next slide we have to draw one figure of this foot over bridge, in which there is 6 panels having the length of 3 meter. Next is live load. Live load means pedestrian loads, which is given as 5 kilonewton per meter square. Next is flooring. RCC floorings having the thickness of 120 mm. Next is floor finish is given as 1 kilonewton per meter square. And next is assume the data if necessary. So students, in the last lecture we have to cover our example up to step number 2, and in the step number 2 we have to find out up to ZP, plastic section modulus. So you can see that in the last lecture we have to cover up to this. Okay, it means in this type of foot over bridge, we have to find out MP. MP means plastic moment. So your plastic moment is 82.5 kilonewton into meter. Okay. Next is VP. VP means maximum shear force. It is also 82.50 kilonewton, and required plastic section modulus, it is 363 cm cube. It means we have to design a cross beam in such a way that our provided ZP is having the greater value of 363 cm cube. Okay, so now first of all you all the students are moved to page number 139. So this is the page number 139, in which we have to check our value of ZP having greater than 363. Okay, so students, you can see that the last second column is our value of ZP, in which we have to take a section in such a way that our value of ZP is greater than 363. So you can see that there are number of sections are there. Okay, but in this example we have to take beam. Okay, in the first example we have to take channel section. Okay, so it is already told that in cross beam we have to take channel section or beam section. Okay, so for beam section we have to check only ISMB, HB, LB and WB. B indicate for beam. But if you take C, then C indicate for the channel. Okay, so you can see that the value of ISHB 250 is 678.73, but our maximum ZP, which is 363, so we have to check and we have to take a section having the value greater than 363. So in this example we have to take ISLB 275. Okay, so you can see that this is our ISLB 275, Indian Standard Light Beam. Okay, So ISLB 275 having the value of 443.09. Okay, so this 443.09 is also greater than 363 cm cube. Now, after the taking a section, this is our trial and error section. Okay, this is not our final section. Our final section is provided when it is passed in moment capacity and shear capacity, which is our step number 3 and step number 4. So this is our trial and error section. So first of all, we have to check our section classification. It means this selected section is having which state. It means there are four classes. First one is plastic, compact, semi-compact and slender. In IS total provision of 800, IS 800, there is three class. Okay, first is plastic, compact and semi-compact. This classification is given on page number 18. Okay, so we have to first of all check the section classification, and for the section classification there are some data is provided from this line. So you can see that for the section properties, capital D. Now what is capital D? So the capital D is the depth of section. Okay, and the depth of section is 275 mm, which is our ISLB section. Okay, next is ZP. So this is our ZP provided. So it is 443.09 cm cube. BF means width of flange. So you can see that for 275 our width of flange is 140. Next is thickness of flange, it is 8.8. Next is thickness of wave, it is 6.4. And one important data which is not given in IS code, which is capital R. Capital R is root radius. Okay, so the value of root radius is given in IS code is not there. It is provided in steel table. So you all the students are moved to steel table, and in ISLB 275 capital R is also called as root radius or ready at root. Okay, ready at root. So all the data will be find out from IS code and steel table. Now we are moving further for the section classification, and in the section classification, first of all, there are two components in I section. Okay, so it is flange and this is wave. So for flange section, you all the students are moved to page number 18, in which your first row is told that outstanding element of compression flange. Okay, so for outstanding element of compression flange, in which there is two rows are there. First one is for rolled section and second one is for welded section. But our this section is rolled section. Rolled means ready-made section, and for ready-made section our equation is B upon TF. Now what is TF? TF means thickness of flange, which is 8.8. But now what is B? B is given as BF by 2. This clarification is given on page number 19, in which there is first figure for rolled section, in which there is a clear indication that your B is BF divided by 2. So students, after calculating all the data, our value is 7.95 epsilon, okay, which is less than your 9.4 epsilon, okay, because for 9.4 epsilon, if the value is less than 9.4 epsilon, then your section is in plastic state, okay. If your value is in the between of 9.4 to 10.5, then it is compact. From 10.5 to 15.7, it is semi-compact. Okay. Now we are moving further for the wave section, and for wave section, you can see that your third column, wave of an I, edge and box section. Now you all know that your I section is symmetric in both the axes. It means your CG is exactly at the center. And when your CG is exactly at the center, it means your neutral axis is exactly at the center. So you can see that on the third column, third row, in which there is a clear indication that wave of an eye, edge and box section, in which there is a one small line in which it is clearly mentioned that neutral axis at mid depth. Okay, so you can see that for neutral axis at mid depth, the equation is d by tw. Now, what is small d? Small d is capital D minus the thickness from the both the side and minus the root radius from the both the sides. And you can see that you have all the data. Capital D is 275, 2 constant, TF is 8.8, 2 constant, capital R is 14 and TW it is 6.4. So after putting all this data, we have to check that our value is 35.84, which is less than 84 epsilon. Okay, now you can see that your flange is in plastic state and your wave is also in plastic state. It means your selected eye section is also in plastic state. Okay, so this is the end of our step number 2, which is the section classification. Now we have to check our selected section is takes maximum moment and maximum shear force. So we are moving further to our step number 3, which is check for moment capacity, and this equation is given on page number 53. So you all the students are moved to page number 53, in which the equation is md is equal to beta b Zp into Fy by gamma m0. Now you all know that our section is plastic because it is already classified in the previous slide that our selected section is in plastic state. So you can see that just below this equation it is clearly mentioned that your value of beta b is 1 for plastic and compact sections. So that's why we have to put down the value of beta b is equal to 1. ZP. Now this ZP is ZP provided because we have to check that our section provided is pass or not. Okay. So this is our ZP and it is 443.09 into 10 raised to 3. This is 10 raised to 3 because we have to convert our cm cube to mm cube. Okay. Next is Fy. Fy is always 250 and gamma m0 is 1.1. So students, after putting all this data, our answer is 100.70 into 10 raised to 6. Now, this 100.70 into 10 raised to 6 is in the Newton into mm. But whenever we have to equalize any value, the unit will be same. And you can see that our moment, which is calculated earlier, is in kilonewton into meter. This is our maximum moment. Okay, so we have to convert this moment into kilonewton into meter by dividing 10 raised to 6. So it is 100.70 kilonewton into meter. It means our selected section takes a maximum moment of 100.70, which is greater than our required moment. It means we are safe in moment capacity. Okay, similar calculation for shear capacity. So you can see that our step number 4 is check for shear capacity. Okay, and in the check for shear capacity, you all the students are moved to page number 59, in which one equation is Vd. So you can see that this is our Vd. So the equation of Vd is Vn upon gamma m0. Okay. Now what is Vn? So you can see that Vn is equal to Vp and your Vp is equal to AV by root 3. If we have to put down this value in this equation, then our equation will be ready like this. It is AV divided by root 3 into gamma m0. Now root 3 is constant, gamma m0 is 1.1, Fy is 250. Now what is AV? So you can see that in this equation for hot rolled section, this is our AV means shear area. So you can see that the shear area may be calculated for major axis. Okay, for eye and channel sections, our area will be like this. It is H into TW. Now what is H? H means our height of section, it is 275 and TW is 6.4. So after putting all this value, our answer is 230.94 kilonewton. But our this answer is not final answer because this answer is multiplied with some value. So this value is 0.6. So this data is given on page number 53. So you all the students are moved to page number 53, in which left hand side bottom last third line, it is clearly mentioned that not exceed 0.6 VD. It means we have to multiply this 230.94 with 0.6. So 0.6 into 230.94, it is 138.54, and 138.54 is also greater than this value. It means our selected section is passed in moment as well as in shear. So students, whenever in any exam you have to check that design for cross beam. So you have to clear that design of cross beam is completed at the end of step number 4. Okay. At the end of step number 2, your design of cross beam is not completed. After checking the moment capacity and shear capacity, your design of cross beam has to be completed. Okay. So this is the end of design of cross beam. Now we are moving further to the fifth step, and our fifth step is load on main members, because after the calculation of cross beam, our main member, which is three main member, top chord, bottom chord and diagonal member. So these three members design is completed in this and next lecture. Okay, so whenever you have to design any structural component, first of all you have to find out loads. Okay, so first of all we have to find out load on main member. So there are three main loads are there. First is dead load from slab. Now whenever you have to design for main member, this is your side view. It means this structure is also same at the another length, which is two length is width of walkway. Okay, you can see that from the top view. Whenever you have to see any structure from the top view, you can see that this is your top view. Okay, and this structure will be occurring at this end if we are see from side view. But if we are see from the top view, your structure will be like this, and we have to start our design of this member. This is your bottom chord, and a similar structure will be occur at the top chord. Okay, so whenever we have to start our main members design, first of all we have to find out loads. Okay, and you can see that this is 4 meter length, so half of the load is transferred to this length and half of the load is transferred to this length. Okay, now from 4 meter, 2 meters load is taken by this length and 2 meters load is taken by these members. Okay, so now we are start our calculations of the load, in which first is dead load from the slab. Now this three value is rho into capital D, 25 into 0.12, because our RCC slab is 120 mm thick, so it is 3 into 4 by 2, which is equal to 6 kilonewton per meter. Next is floor finish. So in the question, it is clearly mentioned that your floor finish is 1 kilonewton per meter square. So it is 1 into 2, so it is 2 kilonewton per meter. Okay, and another third dead load is self weight of all the members. So generally self weight of main member is 1 kilonewton per meter, but whenever you have to check for practical point of view, it is 0.5 to 1 kilonewton per meter for one member. But in your design there is three members, so whenever you have to check for practical point of view, this value is taken in the range of 2 to 3 kilonewton per meter. But 1 kilonewton per meter is okay for not doing any practical point of view. Okay, so You can see that your total dead load is 9, 6 plus 2 plus 1. Now this 9 kilonewton per meter is your unfactored load. So your factor dead load is 13.5. And similarly, your live load is given as 5 kilonewton per meter square. So it is 5 into 4 by 2. So it is 10 kilonewton per meter. And this 10 kilonewton per meter is also your unfactored load. So your factor load is 15 kilonewton per meter. Now, any structural component takes both the loads, dead load as well as live load. So total factor load, which is the factor dead load plus factor live load, it is 28.5 kilonewton per meter. Okay. So students, this is the end of your step number 5 as well as the end of today's session. In the next lecture, we have to complete it our this example and this chapter. Okay. So students, this is the end of our today's session. Thank you.